thank Dan for that nice introduction and John for inviting me. I consider it a real honor. I know how beloved Charlie Frank was, so to be asked to do this, it scares me a little, because in a classroom it's easy, you know, it's truly easy. But here I've got to try to interact at a different level. So I thank you for coming, and let's hope that the story I'm going to tell you will be to some extent interesting. It was fun for us because this is work concerned with, well, it was work done by the group some time ago, and we were very proud of it. But you might wonder why we called it Reinvention of the Wheel. By the way, Dan said John had written the title down as sometimes, right? Reinvention of the wheel can be a good thing. And Dan told me to take sometimes out and shorten the talk. So that's why that happened, okay? But I look forward to giving this talk because, as I said, the work is concerned with stuff that we did, but it also has a connection with the research, the undergraduate research effort here at Seton Hall, and I'm really very impressed by what's done here. It's an amazing department, and I've been associated with it one way or another. I used to go to the parties, which I really enjoyed, right, for a long time. And unless you throw me out, I'm going to keep coming back, okay? So without further ado, let me get to the topic, right? Reinvention of the wheel. Why is it called Reinvention of the Wheel? Well, it's a math talk, right? It's concerned with a mathematical issue. And to put it bluntly, we proved the theorem, which we really liked, which had been proven before, unbeknownst to us, right? But it didn't turn out to be a bad thing as it turns out. I hope you will agree. So for the graph theorists in the audience, I apologize because what I'm going to do is introduce a few basic ideas and perhaps bore those graph theorists in the audience, and I apologize for that. So first of all, what's a graph? For us, it's just it consists of two sets, a finite set of nodes, vertices, points, whatever you want to call them, and a collection of, and there'll be n of those, and a collection of 2-point subsets of V. And they're called edges. And when you draw the picture, you simply take a line and draw it between the 2 points, and you call those edges, right? We do not allow, at this point in the discussion, any loops or any multiple edges. You can't have more than one edge between a pair of points, okay? And so this, by the way, this little example up here is Harari's famous random graph, okay? And the reason it's called a random, I don't know if you know of Harari, but he's a very famous graph theorist. He actually made it popular in this country back in the 60s. He, when he would give a talk, he'd say, let's take a graph at random, and that's what he would draw. So there's absolutely nothing random about it, but that's what he would say. At any rate, everybody knows what the degree of a node is, right? You look at a node and you count the number of edges incident at it, and that's called the degree. So the V that I've labeled up there in Harari's graph has degree 3, clearly. And the next notion is that of a path, because we'll need that in the sequel. A path is just an alternating sequence of points and lines, such that every line joins the point in front of it and the point after it, right? And we insist, if we call it a path, that the vertices or the points be distinct, all right? They all be different. Okay. Now, if you have a path and it's got at least 3 vertices on it, okay? And if the edge that goes from the last vertex back to the 4th vertex actually lives in the graph, and you put it in, you get what's called a cycle, okay? So I've drawn pictures of, trivial pictures of paths and cycles there, okay? All right. Please, by the way, you have any comments to make? This is for everybody in the audience except Dr. Gross, okay? If you have any comments to make or questions, please make them. And by the way, any mistakes here, you blame on him, okay? Because I'm sure we could find a way to justify that. At any rate,
I have a question.
Yes, sir.
Why just Dr. Gross?
Because he gave me a hard time yesterday, that's why. All right, so I want to look at some special graphs with you, because of course these will be used. The complete graph on n nodes. In that case, every possible edge exists between pairs of nodes, right? So look at any pair of nodes, you draw an edge between them. And so I didn't want to draw an arc because I'm not a very good artist. So I actually have a virtual crossing in this particular picture on 4 nodes. That virtual crossing in the middle is not a node, okay? So I got 4 nodes and, of course, 4 choose 2 edges. So that's what we call the complete graph. Fundamental to this discussion is the notion of a bipartite graph. So if a graph has the following property, you can break the node set up into 2 disjoint parts, that is, partition it into 2 disjoint parts, such that all the edges that exist in the graph go between the parts. There are no edges internal to any part, right? Either of the 2 parts. And if that's the case, then you call the graph bipartite, okay? Complete bipartite means that every possible edge that can go between the 2 parts exists in the graph, okay? So, of course, if the number of nodes in part 1 is n1, number of nodes in part 2 is n2, the number of edges is n1 times n2, okay? Now, an important remark is that if, in fact, you know a graph is bipartite and it has the floor of n squared over 4 edges, then it's got to be the complete bipartite graph with equal or almost equal part sizes, right? Part sizes will be floor n over 2 and ceiling n over 2. That's easy to show, okay? All right, another special graph, a tree, right? Tree is acyclic, but it's also connected. What do we mean by that? Given any pair of points, there is a path in the graph that connects those points. So you can get from any point to any other point. That's what we mean by connected. So an acyclic connected graph is called a tree. And it's a nice little induction problem in a discrete math course to prove that the number of edges in a tree is just 1 less than the number of nodes, okay? And then what's a forest? You slap a whole bunch of trees together if you want, right? And those are the, quote, components of the forest. Component means maximally connected subgraph. So I've shown you an example there, and it's pretty easy to show. Number of edges in the forest is just the number of nodes minus the number of trees in the forest, or minus the number of components, okay? All right, good. One more idea before we get to the meat of the matter, the complement of a graph. So if you have a graph G on a node set V, you draw the complement on that same node set, and you include an edge in the complement if and only if it's not in the original graph. Okay, so if you take the famous Harari random graph, its complement consists of just 1 edge and 2 isolated nodes. Okie doke? All right. Enough of that. How did we get involved in reinventing the wheel? All right. Well, at the time this happened, we were working on a vulnerability notion I think I'd like to introduce to you because I think it has pragmatic significance. Imagine a system, and I'm going to use a word Dan Gross told me not to use, right? Imagine a system that has components. These are not connected subgraphs, but components that you can represent as nodes in a graph. And if, in fact, the components have some linkage between them, you draw an edge between them. So, for example, if you had a network of computers and 2 computers were hardwired, you'd put an edge between them. If you have a social network consisting of people, then the linkages, the edges might represent acquaintance, or friendship, or enemies, right? So at any rate, it's a very protean idea. It's a very protean idea to consider a graph modeling a system where the components, right, are the nodes, and the components can fail. Now, if a node fails, the edges emanating from that node become useless. They don't fail, but you just have to remove them, right? They become useless. And originally, back in the old days, in the 60s, when I was reasonably young, okay, the notion that was studied quite a bit was the so-called connectivity of a graph. If a bunch of nodes fail and the surviving subgraph turns out to be disconnected or trivial, you said it was in a failure state. And the minimum number of nodes that had to fail in order to affect that situation was called the connectivity, or point connectivity. We'd rather look at a situation where nodes can fail, okay? You might wind up with disconnected graph, but you got a big piece left, a piece large enough to do the job of the system, okay? And we're going to formalize that by defining the parameter k. So now, in graph theoretic terms, if in fact a bunch of nodes fail and there is at least one component of order k or more, right? Then you'll say you're in an operating state, whether or not the thing is disconnected. That's not a problem, okay? So if in fact nodes fail and all the components have order at most k minus 1, then you say you're in a failure state. That's not good. They're too small, right? They're all too small. So in that particular case, you're interested in the minimum number of nodes that have to fail in order to get a failure state. And that's called the component order connectivity. That's what we called it, kappa sub c super k. And we were studying that idea at the time, okay? And in fact, we were studying a very special case of that, the case where k equaled 2. Now, you might think that this is a trivial case in a way, right? From a pragmatic perspective, because if nodes fail and there's at least one edge left, then you're in an operating state. So in order to be in a failure state, the nodes have to fail and you got to wind up with isolated nodes, right? Bunch of nodes not connected together, all right? Well, that means that to find the minimum number of nodes to produce a failure state, it's the same thing as finding the maximum number of independent nodes in the graph. And the graph theorists know, computer scientists know, that the computation of that beast is NP complete. So this is not a trivial parameter by any means, all right? On the other hand, we wanted to study it from the point of view of, say, synthesis of good networks. So at any rate, let's look at a few ideas associated with this parameter. First of all, you realize that kappa sub c super 2 is less equal n minus 1. If you remove all but one node, you wind up with an isolate, and that's a failure state. So the minimum number of nodes you have to remove in order to get a failure state is certainly less equal n minus 1, right? Well, what if, in fact, kappa sub c super 2 of g is n minus 1? What does that mean? That means that if you remove n minus 2 nodes, you have an operating state. So take any collection of n minus 2 nodes, you remove it, you got 2 nodes left over with an edge between them. So what do you have? You have the complete graph. So the complete graph is the graph that has kappa sub c super 2 equal to n minus 1, okay? Good. So if g isn't k sub n, then in fact kappa sub c super 2 has to be less equal n minus 2, all right? Now, what does it mean for kappa sub c super 2 to be n minus 2? That means if you remove any n minus 3 nodes, so you're left with only 3 nodes, one edge has to still exist in that surviving subgraph, at least one, right? So here are the 3 possible scenarios that you could wind up to get an operating state, right? One edge with an isolated node, 2 edges making up a path, or 3 edges making up a triangle, right? Those are what you can't get is this beast, 3 isolated nodes, right? In fact, if that happens, then in fact you have a failure state. So kappa sub c super 2 is n minus 2 if and only if this does not happen, all right, for some removal of n minus 3 nodes. Well, alternatively, that's the same thing as saying there isn't a triangle. You can't find a triangle in the complement. So we were interested in triangle-free graphs. And we got enthused with triangle-free graphs, and that's what we studied. And that's what the wheel is about, okay, this result that I'm going to tell you about, okay? There's a famous theorem of Turan that deals with triangle-free graphs, okay? It was proved actually published in 1941, which is the year of my birth, which makes it a very old theorem, right? Okay, at any rate, it's venerable. It's a really very powerful theorem. And it simply says if you got a triangle-free graph, you can't have too many edges in that graph. In fact, the number of edges in the graph has to be less than or equal to n squared over 4, the floor of that, n squared over 4, okay? And in fact, if you have floor of n squared over 4 edges in the graph, then that graph must be the complete bipartite graph with equal or almost equal part sizes. Part sizes are floor n over 2, ceiling n over 2, right? Okay? So we played with this a little bit, and we came away with the idea that, in fact, there might be a whole range of e-values such that if you have a triangle-free graph, it turns out to be bipartite. And lo and behold, that's what we were able to prove. So let me tell you what the wheel is, all right? What is the wheel? Oh, we were proud of this, if you remember. It's a long time ago, but we were proud of it. G is triangle-free, and if E lies between the Turan upper bound, floor of n squared over 4, but is bigger or equal to the floor of n squared over 4 minus the floor of n over 2 plus 2, then in fact, triangle-free implies bipartite. And you're going to see that really imposes significant structure on the graph when I tell you what bipartite really means in a few minutes, okay? Furthermore, this lower bound I have here, the lower bound, floor of n squared over 4 minus floor of n over 2 plus 2, that's best possible. So what does that mean? That means that you can find a graph with one fewer edge, floor of n squared over 4 minus floor of n over 2 plus 1, that is triangle-free but not bipartite. So that's what it means to have a best possible result in this case, all right? Okay. All righty. Now, before we can really, I want to discuss the proof of this theorem because I think we did it in a nice pedagogical way. In fact, what we did was we proved the theorem, our theorem and Turan's theorem in an interleaved way, so that it turns out to be very nice and smooth to get through the 4 statements. I wasn't the sole author here, so I'm not bragging, okay? I'll brag about my friends. At any rate, what I'm going to show you now, and forgive me, graph theorists, but I'm going to prove that if G is bipartite, then in fact G can't have any cycles of odd length. And conversely, if G doesn't have any cycles of odd length, then G is bipartite, okay? So any result that says triangle-free implies bipartite is saying what? If you simply don't have any triangles, you don't have any odd cycles, right? That's kind of powerful when you think about it from that perspective. All right, so let me first prove the necessity of the non-existence of odd-length cycles, okay? Suppose you have a bipartite graph and you have an odd-length cycle. Now, please, there's no ambiguity there because the number of points and the number of edges on the cycle is one and the same, right? So odd length would mean that the last point on the cycle has the number 2k plus 1. So I label the nodes on the cycle in a clockwise fashion. And then I go to the graph that's supposed to be bipartite, and I examine where the nodes have to be, right? Well, 1 has to be somewhere, so without loss of generality, assume it's up in the top. But then because the graph is bipartite, 2 has to be in the bottom. But then because the graph is bipartite, 3 has to be in the top. And because it's bipartite, 4 has to be in the bottom, et cetera. So by a very simple induction argument, all the even guys, right, are on the bottom, and all the odd guys are on the top. And that's bad. Because you see, there's supposed to be an edge between 2k plus 1 and 1, but that would mean there was an internal edge. And that contradicts bipartite. So that's very simple. That really is nice. The sufficiency is more interesting. So let me get to the sufficiency. And the reason I like to do this is because it's an induction proof where, in fact, the base case also has to be done by induction. So it's a nice theorem, actually, to give in a discrete math class, okay? So how am I going to do this? I'm going to prove that if you only have even length cycles in the graph, okay, then the graph is bipartite. I'm going to do it by induction on the number of cycles you have in the graph, okay? So what's the base case? The number of cycles is 0, right? So if that's the case, you got a forest. It's acyclic, right? And if in fact the number, now we're going to do the base case by induction on the number of edges in the forest, okay? So this is another induction proof. If the number of edges is 0, there are no edges there. Partition it any way you like. There are no internal edges because there are no edges, period. So it's trivially bipartite. Okay, so suppose now that whenever the forest has E edges, E bigger equals 0, it's bipartite. And now let's look at the case where, in fact, the forest has E plus 1 edges. And that means it's got at least one non-trivial tree because it's got at least one edge, right? Now, I didn't say this before, and I should have, and I apologize. If you got a tree, okay, then the tree has at least 2 points that have degree 1, 2 end nodes, at least 2. And that's very simple to prove. You just look at the longest path. And the ends of that longest path have to have degree 1. So every tree has at least 2 end nodes. I only need 1 here, okay, to do this induction. So I take the end node that I find in here away from G. And in so doing, the edge that emanates from it and goes to, say, V, is lost as well, right? Because when you take a node out, so goes the edge. All right, now, the resulting graph, G minus U, is still acyclic. You didn't add any cycles by removing a node. And so it's a forest, but it's got E edges, right? You lost an edge. So the induction hypothesis says this guy is bipartite, so I drew a bipartite picture. Now locate where V is, right? The other endpoint of the edge that's incident at U. If he's in the bottom part, put U in the top part. And I'm done, right? It's bipartite. So that gets the base case done, all right? Main induction hypothesis. True when the graph G has M cycles, all right? Or has at most M cycles. I want this to be strong induction. Sorry about that. This has to be strong induction. So at most M cycles. And necessarily each of even length, because that's the hypothesis, right? There are no odd cycles. All right, so find one, right? In a graph that has M plus 1 even cycles, okay? There'll be at least one. Find one. And number the nodes around the cycle in the clockwise direction, and locate the X that joins 1 and 2K. Take it out, okay? What have we done? In so doing, we've killed at least one cycle. Since you had M plus 1 cycles to begin with, what you have now, once you take an X out, is at most M cycles. Induction hypothesis says this guy is bipartite, right? But now, for the same reason that we gave before in the necessity, 1 and 2K have to be on opposite sides, right, of the bipartite graph. So put X back in, and you still have a bipartite graph. So that's the end of the induction. I need the fact that a graph is bipartite if and only if it has no odd cycles. And that's why we did it. Okay. And if you've seen the proof before, I apologize. But I like it, so I do it. All right. Our pedagogical approach. This is the approach that combines both Turan's result and ours, okay? And I think it flows nicely, so you be the judge of that. Suppose G has n nodes and E edges, then the first thing we'll prove is that if G is triangle free, then Turan's upper bound holds. E is less equal to floor of n squared over 4. That's the first consequence of his theorem. Second thing we'll prove is that if G is triangle free and E lies between our 2 bounds, okay, then G is bipartite. So that's the first consequence of our theorem. The third thing we'll prove is that if G is triangle free and E actually equals the floor of n squared over 4, then G must be the complete bipartite graph with equal or almost equal part sizes. And then finally, the fourth thing we'll prove is that the lower bound in 2 is best possible. We'll construct a graph that has n nodes, and it'll have E equal to floor of n squared over 4 minus n over 2 plus 1 edges. It'll be triangle-free, but it will not be bipontite. Okay, so that's what we're going to do. And forgive me, but I do need a couple of lemmas. And the first one is a pictorial proof. It's so nice and easy, right? I want to get an upper bound on the number of edges in a graph G, provided it has a chordless cycle. What is a chordless cycle? It's a cycle such that if you look at 2 points that aren't consecutive on the cycle, the edge does not exist between them. So there are no internal edges like that, right? So suppose G has a chordless cycle of length R, okay? And we're going to prove that E of G is less equal R plus n minus R times the floor of R over 2 plus whatever edges are left over in the graph G minus V of C. You throw you throw the cycle away, right, to get that little oval there. Okay, so this is kind of simple when you think about it. Since the cycle is chordless, it contributes what? R edges, right, to the count, to the edge count. Now, if you look at a node over in G minus VC, how many nodes can it be adjacent to on the cycle? Well, I claim it's at most floor of R over 2 because you have to avoid triangles, right? It's triangle free. So all those dashed lines can't be there. So you can have at most floor of R over 2 edges going from V over, right? And that's true for every V there. So the number of edges that are due to the cycle and cross between the cycle and the rest of the graph is bounded by R plus n minus R times the floor of R over 2, and then I just add on the remaining edges, right? Now, in the next lemma, I'm gonna substitute for E of G minus VC the quantity n minus R squared over 4, the floor of that, because in anticipation of trying to prove number 1, you know, Turan's upper bound. And a tremendous thank you goes to Billy Kazmazak, one of our family, who found a very terrible typo in this yesterday. And to be honest with you, and I know it's being recorded, it scared the hell out of me, okay? But everything's all right. What I have here now is correct. I don't know. I must have been drinking too much grandpa juice. That's what my granddaughter calls beer, right? Okay, so at any rate, here's the lemma. So I'm going to look at this function of R, right? It's R plus n minus R times the floor of R over 2, plus the quantity floor of n minus R squared over 4. Yes, sir? Oh. Oh. I gave this to, so now you're going to see the error. You know. Oh, Lena's my brain. She's my assistant. And here's what it should read, folks, so you'll forgive me for this. It should read f of R is strictly decreasing for even R. It's strictly decreasing for odd R, bigger or equal 3. The f of R less equal f of 4 is okay. Okay, that's okay. And the proof of 1 and 2, now this line should be changed to read f of R minus 2 minus f of R is equal to 2 times the floor of R over 2 minus 1. So in fact, that difference is always positive, right? But f of R minus 2 should come first, and f of R should come second. I apologize.
1 minus twice.
Yeah, no, but it was the easiest way to change the thing, and I didn't check it. I was a bad boy. Okay. Thank you, Dan. No, he enjoyed that, actually. Yeah. All right, let's get to the proof of 1, if you don't mind, okay? I want to prove Turan's upper bound. So hopefully this will go smoothly, and you'll agree that this is a nice pedagogical approach. If n is less than or equal to 4, you do it by brute force. You just look at all the graphs and make sure that the upper bound for a triangle-free graph holds. So you do it by brute force. Now, the induction hypothesis, you assume that, in fact, this upper bound result is true as long as the number of nodes in your graph, in your triangle-free graph, is less equal k, where k is bigger or equal 4, and you look at a graph that has k plus 1 nodes. Two cases. The first one's very simple. G is acyclic. That means it's a forest. That means it has at most n of g minus 1 nodes, right? Because a tree on n nodes is a forest with the maximum number of lines, okay? So E of g is less equal n of g minus 1, which is, it's very easy to show is less equal n squared over 4. So that's triviality, right, in that case. Second case. Now, this is fun. Choose a cycle, C, of minimum length R in the graph, because it's got at least one cycle. But choose one of minimum length, okay? It's got to be chordless, because if it had a chord, you'd have smaller cycles, right, in the graph. So it's got to be chordless, and the length is bigger or equal 4, right? So by lemma 1, E of g is bounded from above by R plus n of g minus R times the floor of R over 2, plus the number of edges that remain in g minus v of c, right? Now, g minus v of c is also triangle-free, because g is. Consequently, the induction hypothesis, because the number of nodes in that guy is smaller than k plus 1, means that we can substitute for the quantity E of g minus v of c the Turan upper bound by the induction hypothesis. So now I have our good old lemma 2 function. And if I had written it out right, you would understand that that's always less equal f of 4. And lo and behold, what's truly amazing here, and this part is wrong as well. This was supposed to be changed too. And I truly apologize. F of 4 actually equals n squared over 4. It actually equals the floor of n squared over 4. So we're done with that, with Turan's upper bound, okay? Again, I didn't check it, I should have. Proof of 2. So suppose I have an edge count that lies between these two bounds, Turan upper bound and R lower bound. And I want to show if it's triangle-free, then it's bipartite, and we'll do this by contradiction. So suppose it's not bipartite. Then what's it got to have? It's got to have an odd cycle in it, because of what we said before. Odd length, right? But if I choose one of minimum odd length, it can't have a chord. Because if you think about this just for a second, if you have an odd cycle with a chord in it, it breaks that cycle up into 2 cycles, and one of them will have odd length, and it'll be smaller than the minimum one. Contradiction, right? So it's got to be chordless, all right? So we use the 2 lemmas again, okay? In this particular case, I get E less equal, look at the second line, right? R plus n minus R, floor of R over 2, plus n minus R squared over 4, the floor of that. And that follows from, we can replace E of g minus VC by that bracket because of number 1, Turan's upper bound. And so now, I note that this is less equal f of 5. All right? Because R is odd. R can't be 3 because it doesn't have any triangles, so it's got to be at least 5. Right? So this is less equal f of 5. Remember, for odd guys, it's strictly decreasing. Okay. Now, actually, I can change that last inequality to an equality. It's not difficult to prove that f of 5 actually equals the floor of n squared over 4 minus the floor of n over 2 plus 1, which is 1 less than the lower bound. That's a contradiction. So, simple proof, right? Simple proof. Proof of 3. Now remember, we proved 2, right? So triangle-free implies bipartite in that case. So suppose E is floor of n squared over 4, okay? And then we claim that G is that complete bipartite graph with equal or almost equal part sizes. And this is truly easy, because we have 2. The E lies between the 2 bounds. It happens to be equal to the upper bound. So G is bipartite by number 2. And since it's bipartite and has that many edges, we know it's got to be the complete bipartite graph with equal or almost equal part sizes. So 3 is very simple. 4 is fun, okay? we're going to build a graph that has floor of n squared over 4 minus floor of n over 2 plus 1 edges. It's going to be triangle-free, but it's not going to be bipartite, okay? So we're going to take the complete graph, the complete bipartite graph, rather, on n minus 1 nodes with equal or almost equal part sizes, okay? We're going to take that graph, and we're going to take an edge in that graph and insert a node. That little black thing is an additional node. So that increases the node count up to n, right? It's originally n minus 1. Now it's up to n. But look, by inserting a node, you don't create a triangle, and bipartite graphs are triangle-free because they're odd cycle-free, right? So you didn't create a triangle, but what did you do? You took a 4-cycle and you made it a 5-cycle. So this guy has a 5-cycle in him, he can't be bipartite. He's triangle-free. And by the way, now you got to get to the laborious part and count the number of edges, and I won't do that explicitly, okay? It is floor of n squared over 4 minus the floor of n over 2 plus 1, okay? Now, that's the whole story, but well, that's the whole math story, but let me tell you now what happened to us. All right, we proved this, and we were very happy with it. We were good mathematicians in that we did a literature search. And how many of you know who Erdős was? Erdős is amazing, most prolific mathematician of the 20th century. He has over, Dan says about 1,200. 15? Really, I knew it was in excess of 1,000. But papers, he passed away a few years ago, but papers with his name on it still coming out, right? I mean, amazing guy, just an amazing person. We found a paper written by him and a couple of his colleagues, also high-powered people, who proved the following kind of, it was 91, who proved the following result. If you have slightly fewer edges than the Turan upper bound, okay, then triangle-free will imply bipartite. They never gave the lower bound. And of course, if they didn't give the lower bound, they couldn't have proved it was best possible, right? No citations to anything before it. So we arranged to speak at Kalamazoo. I know it's only famous for the song, right? But actually, in the old days, every 4 years, there was a Kalamazoo conference, very popular among graph theorists, right? And we were proud and happy to be able to give the talk there, right? About 20 minutes before I had to go in and give this talk, John Sockerman Jr. had been to the library. He was my thesis student in those days, came running over and said, "Pop, you got to look at this paper." I looked at the paper and I turned white because it had the theorem in it exactly as I stated it, the wheel, right? It had the theorem in it, and who do you think it was by? Erdős all by himself. And it was published in 1962, 29 years before. He had forgotten. And it wasn't cited. So I said, what am I going to do? Maybe I'll run away, I'll get back in the car, and I'll go home. I went in and I apologized, and I said, look, I think the presentation is pedagogically sound. You could use it in a graph theory course. If you like, I'll tell you about it. And they said, okay, nobody left. And I think, I'm fortunate today, too, because nobody's left yet. At any rate, I gave this talk, and one of the mathematicians at the talk, Paul Ballister, said some nice things about the result. And then he got together with another famous mathematician, Bela Bolabash, who does functional analysis and combinatorics, which is a wild combination, right? And they did a generalization of this result that, I'm going to show you now briefly. I'm not going to prove it. I'm just going to tell you what it says. But in order to tell you what it says, I got to tell you what an R-partite graph is. Well, that's kind of trivial, right? You partition the set V into R pairwise disjoint parts. All the edges that exist have to go between parts, no internal edges, all right? If you got all the possible edges between parts, you call it complete R-partite, okay? Simple? One more idea. Suppose you use the good old division algorithm and you divide n by R, okay? You divide n by R. And you get, of course, a remainder m, which is bigger equals 0, less equal R minus 1. Now, it's easy to see that, in fact, you could partition the node set into R minus M parts of order floor n over R, and M parts of order ceiling of n over R, okay? And I'm sorry, I'm wondering what I said there. Oh, yeah. Okay, what I want to do, though, is I want to add all the possible edges between those parts. So I want to form the complete bipartite graph, R-partite graph with equal or almost equal part sizes described here. And TR of n is the number of edges in that graph. T for Turan, of course, right? Now, T sub 2 of n is floor of n squared over 4, right? And what you should notice, by the way, is that no R-partite graph can actually contain in it an R plus 1 complete graph. Because by the good old pigeonhole principle, one of the parts would have to contain at least 2 points. But they're not allowed to be adjacent. So you're not going to get a KR plus 1 in an R-partite graph. So here's what these guys proved, okay? The analog of triangle free in this case is KR plus 1 free, okay? So if your graph is KR plus 1 free, and the number of edges lies between the Turan number minus the floor of n over R plus 2 and the Turan number up top, then G is R-partite. This is a direct extension of what we did when you take R equal to 2. It's a very pretty result. So, but I'm not as enamored with that one as I am with the next one, because the next one is the result of undergraduate research here at Seton Hall. And here are the culprits, right, who were involved with their tutor, Dr. J.T. Sockerman Jr., right? And they did a really, really pretty result that extended the wheel to multigraphs, okay? So what is a multigraph? You still don't allow loops, but now you allow multiple edges between pairs of points. And you define the multiplicity to be the number of edges between a given pair of points. So if it's 0, there's no line there. If it's 1, it's the ordinary situation. If it's 2, you draw 2 edges between, and so on, right? Okay? So here's what these folks proved, and a really nice result, okay? I'm going to let script M sub mu be the class of all multigraphs, M, with maximum multiplicity at most mu, right? So you look at that class of graphs. So no multiplicity of any edge is bigger than mu, okay? And if you take a multigraph from that class and it's triangle free, and the number of edges in that multigraph lies between mu times the quantity n squared over 4 minus n over 2 plus 1, close parentheses, plus 1, but bounded from above by mu times the floor of n squared over 4, then M is bipartite, okay? And also the lower bound is best possible. And if you take mu equal to 1, you get the wheel, right? It's really quite pretty, and I'm so happy that this was done. There's one remaining thing. By the way, the moral of the story is that if we didn't reinvent the wheel, perhaps this might not have been done. It may have anyway, but these two generalizations came out of the fact that we made the mistake of not knowing about the Erdős proof from '62. So that's why reinvention of the wheel can be a good thing, all right? But as I understand it, John, there has been some work done on generalizing the Ballister-Bolobach theorem to multigraphs, right? But it's not complete. Please complete it, all right? And then the whole story will be done. I thank you very much for your kind attention, and I'm sorry I can't, what was that, 45? Is that all right? Okay, good. Thank you.